So when you think about AI, what's the first thing that pops in your head? For most of us, it's probably these huge, sprawling data centers, right? But what if I told you that AI also lives on a teeny tiny chip, one that can run for years on a little coin battery? Today, we're going to explore that entire world where AI lives, from the massive cloud all the way down to that tiny chip. And that brings up a really obvious question.
I mean, it's a fair question, right? The cloud has, for all practical purposes, unlimited power. It's like this one gigantic, all-powerful brain. So why would we ever go to the trouble of putting AI anywhere else? Why isn't every single AI model just running in a massive data center somewhere?
Well, the answer, believe it or not, comes down to the basic laws of physics. It turns out there are these three, let's call them unseen walls, that make a cloud-only world totally impossible. First up, you've got the speed of light wall. I mean, data just can't travel from a data center to your device and back again instantly. It takes time. Then there's the power wall. You see, these chips get so hot that we literally can't make them run any faster without them melting. And finally, there's the memory wall. You can have the fastest processor in the universe, but it's totally useless if it's just sitting around waiting for data to show up. And here's the kicker. These are problems we can just solve with better software. Nope, these are fundamental limits of our universe, and they force us to get creative.
So to get around those walls, engineers have come up with a whole spectrum of solutions. Let's start our journey at one end of that spectrum, moving from that massive, thinking central brain of the cloud and work our way towards the super fast, almost automatic local reflex of what we call the edge.
Okay, first up, Cloud ML. This is the one you're probably most familiar with. It's AI running in those giant centralized data centers we talked about. And the trade-off here is super simple. You get access to almost infinite computational power, but you have to pay the price of network latency. And that's just the time delay it takes for your request to travel all the way to that data center, get processed, and for the answer to come all the way back. The AI is incredibly smart, but it's also really, really far away.
And when I say powerful, I mean it's hard to even wrap your head around it. A single one of these AI systems, a Google TPU pod, can perform over an exaflop. That's a 1 with 18 zeros after it, a billion calculations, every single second. But all that insane power comes at a cost. It can guzzle over 3 megawatts of electricity. To put that in perspective, that's enough to power thousands of homes. The scale is just, it's mind-boggling.
So that brings us to Edge ML. This is the direct answer to the cloud's distance problem. The whole idea is to move the computation closer to where the data is actually being created, right to the edge of the network. So think of powerful servers located inside a factory, or maybe in the back room of a retail store.
A perfect example of this in the real world is an Amazon Go store. You know, the ones where you just walk out. They have hundreds of cameras tracking everything that's happening. Now imagine trying to send all of that high-def video footage up to the cloud to be processed. It would be incredibly slow and cost a fortune. So instead, they have local edge servers that handle all that video processing right there, inside the store. This makes it way faster, way cheaper, and honestly, a lot more private, since sensitive video of customers never even has to leave the building.
But we can get even closer to the user than that. So let's keep moving down the spectrum. We're going from a server in the back room all the way to the device that's literally in your pocket, and even to sensors so small they're practically invisible.
Next up is mobile ML. This is the AI that lives right on your smartphone. Now, the challenge here is completely different. Everything has to run on a battery, which is a huge constraint. This is all about enabling things like personalization and working completely offline. Think about the incredible computational photography that makes your phone's camera so ridiculously good. That's all happening right on your device, all while just sipping power.
And finally, we get to the most extreme end of the entire spectrum, tiny ML. We're talking about AI running on tiny microcontrollers that might only cost a few bucks. Here, the absolute #1 priority above all else is energy efficiency. These are what we call deploy and forget devices, things that can run for years on a single tiny coin battery. It's amazing.
Okay, so let's put this all together and look at the big picture. This table really lays out all the trade-offs perfectly. Just watch what happens as you go down the rows, from cloud all the way to tiny ML. Look at latency. It drops from maybe half a second all the way down to a single millisecond. And power consumption, it plummets from megawatts to milliwatts. That's an incredible drop. And notice how privacy gets stronger and stronger, simply because the data doesn't have to leave your device.
Each of these categories is a champion in its own right, perfectly optimized for a completely different job.
You know, the difference between the two extremes is that's just staggering. Just look at this comparison. Cloud ML can have over 100 terabytes of memory. A tiny ML device, it might have just a few hundred kilobytes. If you do the math, that's a difference of about 250 million times. We're going from megawatts of power, enough for a small town, down to fractions of a single watt. This isn't just a difference in degree, it's like we're talking about two completely different universes of computing.
But here's the real secret. The most powerful, most sophisticated systems, they don't just choose one of these. Nope. They actually use all of them together to get the best of all worlds. And we call these hybrid systems.
Your voice assistant is the perfect example of this. So think about it. First, there's a tiny ML chip that is always listening for the wake word. Hey, whatever. And it does this using almost zero power. That's step one. As soon as it hears you, it wakes up your phone's main processor, that's the mobile ML, to handle a simple private command like set a timer for 5 minutes. That's step two. But if you ask a really complex question, something like, what's the weather going to be like in Tokyo next Tuesday? That's when it calls in the big guns. The query gets sent up to the cloud ML for some serious heavy-duty processing. That's step three. It's this beautiful, efficient, tiered system.
Okay, so this is all great, but how do you actually choose the right AI for a given job? It might sound complicated, but it's really not. There's a pretty simple decision framework you can use. All right, the very first question you have to ask yourself is all about privacy and security. Can my data leave this device? I mean, if you're dealing with sensitive medical data, or maybe some proprietary information from a factory floor, the answer is often a hard no. And right there, that single answer immediately tells you you need local processing. You're already narrowed down to edge, mobile, or tiny ML.
Okay, next up, you ask about speed. Do you need an absolutely instant, real-time response? Think about something critical, like the emergency braking system in a self-driving car. If the answer is yes, if you need a response in less than, say, 10 milliseconds, well, the cloud is just not an option. It's physically impossible. The speed of light itself won't let the signal get there and back in time. Simple as that.
So, once you've figured out that you definitely need local processing, the final question really comes down to your budget, both for power and for cost. Does the job you're doing need the serious horsepower of a full-on edge server that's plugged into a wall? Or are you building a tiny, battery-powered sensor that has to last for years and years? The answer to that question is going to point you to the perfect solution on the local spectrum.
And this all leads to the big idea of this whole explainer. All of these physical walls we talked about, the speed of light, the limits of power and memory, they aren't just limitations. They're actually the very things that force creativity. They are what drives all the innovation we see across this entire fascinating spectrum.
So that really leaves us with one final thought to chew on. We've seen how these trade-offs have shaped the AI landscape that we have today, but as AI continues to weave itself deeper and deeper into the fabric of every single object around us, what's going to be the next great challenge? What's the next big trade-off that will define the future of intelligence?